Okay, now we've talked about the idea of probability, and we've talked about simulation to help kind of calculate the idea or try and get an idea of what the probability is of something occurring when we don't really know anything about it. A simulation kind of helps us figure out what the probability might be. We're going to start talking about probability models and theoretical probability now. So the probability models are really nice because we don't have to go through that simulation to figure probability. We now can use our mathematical models that help us determine probability. So for a true probability model, you need these things. So our probability model must consist of a sample space, which is a list or a picture of all possible outcomes, and then the probability for each outcome. And so sometimes they're even, sometimes they're not. And so what we have as a sample is the sample space for rolling 2 dice. And so you could have here's one outcome. The first dice could be 1, the second dice could be 1. And so it lists all the possible outcomes. Now in this situation, the probability is even for each outcome. And that's not always true. Sometimes they're not always even. The reason why this would be even is because it would usually be a fair die. It's not a weighted die, it's a fair die. And so each outcome is equally probable. And so when I can look at this, I can figure out how many different outcomes there are. So 1, 2, 3, 4, 5, 6. And then I've got another row 6. So 1, 2, 3, 4, 5, 6. So 36 outcomes, which are equally probable. So each one has a chance of 1 out of 36. So then when I start asking you, well, what's the probability of getting a sum of 5? Meaning, what's the probability that when I roll 2 die, they're going to add up to be the number 5? And so then I'm going to look at how many of my outcomes add up to be the number 5. So let's see, here's a 5, and here's a 5, and here's a 5, and here's a 5. So 4 of my outcomes add up to be 5, which means the probability of getting 2 dice that add up to be 5 should be 4 out of 36. Now, for our purposes, we reduce the fraction. So both of these can be divided by 4, which is a 1 out of 9 chance. Mainly because our brains make more sense of something that is either as a reduced fraction, where it's low numbers, or turned into a percentage. It just makes more sense to us. Okay, so we've got some terms that we're going to talk about. And the first one, which is a really important one, is what we call the complement. And the complement of an event is the probability of an event not occurring. And so it's kind of like everything else. And it comes from the idea that all probabilities of a true probability model should add up to be the number 1. So if I need to know the probability of an event not occurring, I can take 1 and subtract the probability of an event occurring. And so that is this formula right here. Now the complement is labeled as whatever the event is with a little c up top, a superscript, because it's saying I don't want this happening. So the event and then the little c means not occurring. So for example, using the 2 dice example, what's the probability that the sum is not 5? So I would take 1 and I would subtract the probability that the sum was 5, which we had 1 and a 9. And so then I would change 1 to 9 over 9, because when I'm adding and subtracting fractions, I need a common denominator, which gives me a probability of 8 over 9. So the probability of getting 2 dice that do not add up to be 5 would be an 8 out of 9 chance. Okay, the next definition that we're going to talk about is mutually exclusive. And so two events are mutually exclusive if they cannot happen at the same time. So, for example, if we're looking at the dice, the probability that both of them are even, so both numbers are even, and the probability that they add up to 5. Why? Is because if they have to add up to 5, one of the numbers has to be odd. So if you're looking at 2 and 3, they add up to 5, 3 is your odd number. If you're looking at 1 and 4, 1 is your odd number. So there's no way that both of these can occur at the same time. For example, the probability of getting an A in the class and the probability of getting a D in the class. You can't have them happen at the same time. You can't have an A and a D in the class. Your grade's either A or your grade is D. And those would be mutually exclusive. Now, two events are inclusive if they can happen at the same time. So the probability at least one number is 2 and the probability the sum is even. You can have one number of 2 and then when you add the 2 up, the answer could be even. They can happen at the same time and that's our inclusive. So mutually exclusive cannot happen at the same time, inclusive can happen at the same time. Now here's our rules of probability and we've alluded to quite a few of them. Like all probabilities between 0 and 1, we talked about that last time. All possible outcomes must add up to 1. So that's how you can tell if it's a true probability model, because if you add up all those probabilities, they should add up to be 1, or else it's not a true probability model. If all outcomes are equally likely, the probability of event A occurring could be P of A, so probability of A is the number of outcomes corresponding to that event. So how many times did I get them adding up to 5? I had got that 4 times out of the total number of outcomes, 36. So that's our rolling die problem. We had 4 that added up to 5 out of 36 possible outcomes, and that gave me my probability. But again, that only works if they're equally likely. And in chapter 6, we'll start looking at events where they're not as equally likely. If events are mutually exclusive, then, now this is a really important rule right here, the probability of A or B is equal to the probability of A plus the probability of B. So the probability of getting an A in the class, the probability of getting a B in the class, the probability of getting an A or a B would be just adding those two up. Because you can't have an A and a B at the same time in the class. Your grade is either A or your grade is B. So we can add those up to find the probability of getting A or B. But if they are inclusive, we have to take into consideration now the fact that we have kind of overlapping occur. So let me think. So a great example that we like to look at for inclusive is a deck of cards. What's the probability of getting an ace or a red card? Because a card can be an ace and it can be a red. So I can't just add probability of ace and the probability of red. Because I've got cards that are being counted twice, like the ace of hearts and the ace of diamonds. The ace of hearts is being counted here, but it's also being counted here. And I can't count the card twice because it's really just one card. So what we do is we subtract those that are in both. So because I counted the ace of hearts here and here, I'm going to subtract one of those ace of hearts. And then I also had the ace of diamonds was counted here and here. So then I'm going to subtract one of those ace of diamonds to account for that double dipping. Because we can't count the card twice. It's only one card. So we only count it once. And so that's where we get this idea of if they're inclusive, I have to subtract what we call the repeaters, the ones that were counted twice. Okay, so Imagine we're flipping a fair coin 3 times. Give the probability model for this chance process. Okay, so our probability model has to have a sample space. So we've got to look at all of our possibilities. So if I'm flipping a fair coin 3 times, I could have heads, heads, heads. Or I could have heads, heads, tails. Or I could have heads, tails, heads. Or heads, tails, tails. Or I could have tails, tails, tails. I could also have tails, tails, heads. I could also have tails, heads, tails, or tails, heads, heads. So these are all my possibilities. Now the idea is if this is a fair coin, I also have to list the probability of each event. So because it's a fair coin, all of these events should be equally likely, which means each event has a probability of 1/8, because there are 8 total, and the probability of getting one of those, which should be 1 out of 8. Okay, so now what we have is a sample problem where the probability is not even. So they give us a table. So randomly select a student who took the 2010 AP Stats exam and record the student's score. Here's a probability model. So they took all the kids who took the 2010 AP Stats exam and recorded the probability of picking a student who had a score of 1, 2, 3, 4, and 5. How can we show that this is a legitimate probability model? Well, the first thing is all probabilities are between 0 and 1. Now the second thing is we have to check to see if they all add up to be 1. That's our other big concern. So we're going to grab our handy dandy calculator and we're going to add up all those probabilities. So 0.223 plus 0.183 plus 0.235 plus 0.224 plus 0.125 gives me 0.99. So now the question is, does it add up to 1? Well, here's kind of the problem. It doesn't add up to 1, but because of rounding error, they rounded their decimals. Is it possible it could add up to 0.99? So we have to ask ourselves about this. Based on this, is it a real true probability model? And I would say this is close enough. We shouldn't be off by more than 0.01 though. So you have to be careful about that. And you really may want to look into, is this a rounding error or not? Or did I use my calculator wrong? So we could always double check. 0.223 plus 0.183 plus 0.235 plus 0.224 plus 0.125. Yep, we got 0.99. So just a little something to kind of talk about. Does it really add up to 1? Does it not? So that's why I purposely picked this problem. Okay, so yes, we'd say it is a good probability model because 0.99 is good enough. Okay, find the probability the chosen student scored 3 or better. So now we have to think about this situation. A 3 or better. Is it possible to score a 3 and a 4 on the AP Stats exam? Or are these mutually exclusive events? Well, you shouldn't be able to score a 3 and a 4. What you score is what you score. So if I want the probability that a person scored 3 or better, and these are mutually exclusive events, I can add up all these probabilities, and that should tell me the probability of scoring a 3 or higher. So I'd add up the 0.235, the 0.224, and the 0.125. Or I can use the complement idea. I could do 1 minus what I don't want, 0.223 minus 0.183, and that should tell me the same answer. So we can use this idea of complement to help make our computation just a little bit easier. 1 minus 0.223 minus 0.183. So here I got 0.594. And here I got 0.235 plus 0.224 plus 0.125. I'm going to be off a little bit. 0.584. Why am I off a little bit? Why is this happening? Because when I checked to see if it was a legitimate probability model, did it add up to 1? No. So when I did this, I really should have done, instead of this, the 0.99. Because on my legitimate probability model, I noticed that there was a little bit of a rounding error and it didn't add up. So then this would be really 0.584. So just a little something to think about, keep in your mind. Complements are nice, but you've got to be careful about them. Okay, next problem. Choose an American adult at random. Define 2 events. So event A is that the person has a cholesterol of 240 or above. And event B, the person has a cholesterol of 220 to 239. According to the American Heart Association, the probability of A is 0.16 and the probability of B is 0.29. Why are they mutually exclusive? Well, because can't have a blood value of 240 plus and 220 to 239. You're in one range or you're in the other. It cannot be both. That's why they're mutually exclusive. And by definition, mutually exclusive, they can't be in both groups. So, say in plain language what the event A or B is. What is the probability of A or B? So A or B means helps if I can spell cholesterol. So the cholesterol level is between 220 and 239 or 240 and higher. We could even say that probability of A or B is cholesterol level is 220 or higher, because that really takes over the whole thing. So if you want to go just straightforward, this is my A, this is my B, or backwards, B and A, or you can envelop it in one idea. Cholesterol level is higher than 220. That would be a more short, sweet, to the point. But that takes real understanding of what they're asking you, rather than just saying it's A or B. So you can tell those differences by reading people's responses. What is the probability of A or B? Well, since they're mutually exclusive, this probability should be A plus B added up. So 0.16 plus 0.29, which is 0.45. Why doesn't this add up to 1? Well, because we also have other options, and those options are event C. So if C is an event that a chosen person has normal cholesterol, which is below 220, what is the probability of C? Well, theoretically, it should be whatever probability is left. So 1 minus 0.45. And that's assuming those are not rounded with some error, but it gives us about 0.55. And so we just use that because that's what we know.